So let me introduce Seth and the presentation he's going to give. I already read all this stuff. Seth holds a Department of Energy, Fusion Energy Sciences postdoctoral fellowship in Princeton University's Department of Astrophysical Sciences. He's currently conducting research at the Princeton Plasma Physics Laboratory, which is one of the DOE laboratories, primarily focusing on how turbulence behaves in compressing systems. Dr. Davidovits' work may have applications in inertial confinement fusion and Z-pinch experiments and in astrophysical plasma such as molecular clouds. He earned his PhD in plasma physics from Princeton in 2017, and he is a DOE CSGF alumni from 2010 through 2014. So the floor is yours.
Thank you for the introduction. And yeah, so today I'm going to tell you, give a bit of an overview of some of the work that I did for my thesis. And this work is on basically predicting and how we might utilize then turbulence in compressing plasma. So first, I want to say thank you to Fred Howes and his family, to the CSGF Fellowship and the Krell Institute. The fellowship had a really big impact on my graduate career and was definitely very enabling of this research. The Howes Selection Committee, and then my thesis advisor and experimental collaborators at the Weizmann Institute of Science Plasma Laboratory, and then finally the other funders of the thesis research. So today, as I said, I'll be talking about turbulence in compressing plasma. So there's three ingredients here. We have a plasma, so here's plasma in a neon bulb. We have compression. Here's our Coke can. It's been compressed, so its volume has been reduced. And then we have turbulence. So we have some swirling flow field here. And these three ingredients coexist in a variety of both laboratory and natural systems. So I'm going to tell you a bit about this problem in general, and then some applications that we had in a few different systems. And two of those systems, which I'll talk about, are inertial confinement fusion. And here you're compressing with lasers. And then I'll also talk about astrophysical molecular clouds. And in this case, this compression of the plasma happens through gravity or through some external pressure forcing. So plasma, just so we're all on the same page, we have a gas that's at least partially ionized. And for the sake of this talk, you can think of it basically as a gas or a fluid, but with some additional effects, and I'll highlight those where they're important for what I'm talking about today. And so we have a variety of natural plasmas and also plasmas in the laboratory. And one of the main plasma laboratory applications is trying to do fusion energy experiments. So in the laboratory, this is fusing two isotopes of hydrogen to make helium and a neutron and release a bunch of energy. And in all of these areas, we have high temperatures. And those high temperatures mean that whatever matter we have will be ionized to a plasma state. So today I'm going to focus a lot on the plasma viscosity and its impacts. So plasma has much stronger temperature, T, and dependence, and also has a viscosity that depends on the ionization state Z. So we can see if we look at the plasma viscosity, it scales as the temperature to the 5/2. And if you compare it to like a typical model for a gas viscosity, this is a much weaker scaling with the temperature. And then the viscosity is also dependent on the charge state. So basically how many electrons we've stripped off of the ions in our plasma. And so just conceptually, we can think, OK, as we heat the plasma, we go from pouring something like this water to pouring more like this honey. And then if we're ionizing our plasma, we're tending to go in the reverse direction. Then another ingredient is turbulence. And for the sake of this talk, I won't go too much into particular properties of the turbulence. It's more just the fact that we have some sort of disorganized flow in the gas, and I'm going to focus mainly today on the energy that's in this flow. And so you'll hear TKE. This is the turbulent kinetic energy, and it's basically just how much energy is in the flow that's in this plasma that's compressing. And the energy can be in other components in the plasma, so I'll make a distinction today between energy in the thermal component, which is basically some sort of random local motion of the plasma, and then energy in the flow, which is that all the particles, if you look locally, are going in the same direction to some degree. And in general, you'll have some combination of this random thermal motion and this directed flow when you look locally. So just to set up the problem conceptually that I'm studying, consider you have two plasmas, and they have the same initial energy. On the left, we have plasma at some volume, some density, and some temperature, and all the energy in this plasma is in this random motion in the temperature of the plasma. And on the right, I set up a similar plasma, but I instead put, say, 3/4 of the energy into this thermal energy, and 1/4 of the energy into some sort of disordered flow in this plasma. And then I'm going to compress this plasma on the left, and say I do it adiabatically, so I'm assuming that no energy is lost from the plasma as I compress it, and assume it acts as an ideal gas. Then many of us will be familiar with the ideal gas law, PV equals nRT, and we can calculate basically the final temperature of this plasma after I've done this compression. We can calculate how much energy I put into it. Basically, we know the things that we want to know about the final state after this compression. Now I do the same compression to this plasma on the right, and then I want to ask, what is the final partition between thermal and turbulent energy at the end of this compression? How much energy did I put in to this plasma in doing this compression? And now I don't have something like this to tell me what happened. And basically, in this talk, in various ways, I'm trying to fill in our work, fill in this question mark in a variety of different, both generally and then in a variety of different applications. And this then will depend on things about the compression, but I'll try and this is the problem I'm working on, and then applying results of this problem in various areas. So why does this partition matter between the temperature and flow? So understanding this partition matters for different reasons in different applications. And here's a list of some of them, and some of them I'll talk more about then as they come up in the applications that I discuss. For one, it can affect energy transport in your plasma. If you have all this flow, it can also affect particle transport or mixing of materials. It affects fusion and X-ray production, which I'll talk about. It can confound your diagnostics if you're trying to measure something about this plasma and you have no idea how much flow you have. This can, depending on what your assumptions go into measuring, you might get the wrong answer. And then some other effects, which I'll discuss as well in the context where they arise. So I'm not the first person to look at what happens when you compress turbulence. There's been a substantial amount of work on this in the fluid and gas literature, in aerodynamics and combustion. So here is here's some simulation results from 1996. They're basically looking at a cylinder in an internal combustion engine, and like you might have in your car. And basically, the gas in the cylinder, when it's drawn into the cylinder, will pick up flow. And then the cylinder compresses before you combust. And that compression will affect this flow. And then you'll have this basically turbulence in your cylinder. And that can affect things like how the combustion progresses and the efficiency of the engine, say. So this is a problem of interest. And for the purpose of this talk, two key takeaways from these previous studies is that the turbulent energy can grow when the turbulence is compressed. Basically, the compression acts as a forcing on this turbulence, and that the time scales of the compression are important. So if you compress very quickly compared to the time on which the turbulence would normally dissipate, that's when you can dump a bunch of energy into the turbulence. Now, if you compress slowly compared to the time on which the turbulence would normally dissipate, then basically the turbulence doesn't see your compression, it just dissipates, and then you basically compress it after it's gone. So there's also been some work on this problem in astrophysics, which I'll touch on, but in plasma specifically, there was not that much done. So what's new in a plasma compared to these previous studies? For one thing, the size of the compressions that we're considering is drastically different. So in this combustion engine, for example, you're compressing the volume by, say, a factor of 10 in the compression. In something like I'll talk about later at the National Ignition Facility experiments, you're compressing the volume by a factor of 10,000, give or take. Another is how much turbulence you have compared to the other energy components in the problem. So I'll touch on both these Z pinches and molecular clouds. And in both of these problems, you have so much turbulence that actually the energy in the flow is more than the energy in the thermal component. And this ends up meaning actually that your turbulence is supersonic. And this has a lot of effects on what happens when you compress. Another way, which I've highlighted one, is that the properties and processes that go on in plasma can be different than in a neutral gas. So I'll talk quite a bit about viscosity today. And this difference alone can cause existing models for fluid or gas turbulence behavior under compression to fail. But of course, then there's other things that can come in a plasma, like magnetic fields or radiation, which I won't touch on today. But that can also make a difference versus previous studies. So we're trying to fill in this gap in understanding what happens to this plasma turbulence when we compress. And the way that I've been working on this is basically through sort of medium, modest scale simulations paired with analytic calculations. So these simulations, I'm basically taking some box. It has some initial turbulent flow field in there and some amount of thermal energy. And then I'm going to compress it and study what happens. And this box has a side length L. And that side length will shrink in time as I compress, basically, in the simulation. And today, I'll basically only talk about how the turbulent energy changes under this compression. So I'll be showing some plots like this. And it'll always be the turbulent energy on the y-axis, and then the side length of this box on the x-axis. And so in these examples, you're starting with a side length of 1, and then you're compressing as you move to the left, and you can see basically how the turbulent energy changes. So what is this plot showing? I talked before about how the viscosity in the plasma is sensitive to both the temperature and the ionization state. And of course, both of those can be functions of the compression. So in the temperature case, this is basically asking what's the balance of heating and cooling processes that are going on in this plasma as we compress, and that controls, does the temperature grow, does it decrease as we compress, and similar things can be said for the ionization state. And so this means that between the two of these and the possible balance of influences under the compression, a wide variety of behaviors for how the viscosity acts under compression are possible. And so in this plot, I'm basically showing 3 these three identical compressions, the same initial condition, compressing at the same rate, and but the only difference being how does the viscosity scale as the compression progresses. So in the top line, I'm basically starting at the right, energy of 1, and I'm compressing, moving to the left, and you can see that I'm initially amplifying the energy in this turbulence, and then it basically saturates at some level. And then in this middle case, I'm initially amplifying the energy as I compress, and then it turns over and starts to decrease. And in the bottom case, it almost doesn't amplify at all before decreasing. And basically, this is just a way of saying that this viscous behavior is important and something that we need to care about. And then I'm going to talk in specific applications about how this comes up. So the first application I'm going to talk about is inertial fusion. So this is basically, you can think of trying to achieve this fusion reaction in the laboratory. So it's interesting both as a basic science pursuit, possibly for energy, and then for what's known as stockpile stewardship. And in order to get this inertial fusion to work, we need high temperature, and this means we'll be a plasma. And then we also need a high density. And we need a high density because this fusion product, we want to stop in our plasma and heat it. And this way we can have basically a self-sustaining reaction where we're not trying to only putting in energy from the outside. The energy that's being generated there can help us basically burn more of the fuel. So how do we do this? We take a room full of lasers, and then we have a target chamber with ports to shoot the lasers in. We shoot in these lasers into a gold cylinder. They hit the cylinder and generate X-rays. These X-rays hit this outside of this capsule, and this capsule is filled with our fusion fuel. And when the X-rays hit the capsule, it's a bit like we're defending our planet from asteroids, and we're basically ejecting material off the outside of the capsule, and a back reaction, like a rocket, pushes the capsule inward. So these X-rays hit the outside, they eject material off the capsule, and the back reaction compresses it. So we start with some capsule filled with fusion fuel like this, and then we're going to compress it down to this little point. And at the end, for fusion, what we hope we have is that we have a 50 million degree plasma hotspot in the middle that's very dense, 100 grams per cubic centimeter. And this is going to be fusing. And the question is whether we have what this ideal picture is. So this is results from highly detailed 3D simulations and of this sort of implosion, and they basically see near the end that they have this complicated flow field in the plasma that's being compressed. And this matters for a few different reasons. So one is you have this hot spot where you're trying to make the fusion, and it's surrounded by both non-fuel material, the plastic of the capsule, and also colder fuel. And you might worry that this flow field can help introduce those materials into your hotspot and ruin your fusion. Another thing I mentioned briefly before was that if you're trying to measure what is going on, this can confound your diagnostics. And then a very direct way this could be a problem is that it's in some sense this energy in this motion here, if we're trying to get fusion, is wasted because it won't actually help us to fuse. And we can explain this. So if we have thermal energy in our plasma, then this is this sort of randomly directed motion. And that randomly directed motion means that these ions will have a chance to collide, and we need them to collide to make fusion. And coincidentally, also, this will make more X-rays. If it's cold and flowing, then basically there's less relative motion between the particles and less collisions to get fusion to work. It also means if it's cold that there's fewer X-rays. And this X-ray difference I'll mention then later. So in these experiments at NIF, it's not totally clear whether the turbulence will be an issue or not for achieving what they want to do. Basically, it's somewhat sensitive to exactly how the compression progresses, whether you end up in sort of you look like smooth, or you have this turbulent flow. But in any event, to check a single case is a very high resource investment. So like millions and millions of CPU hours to do one initial condition and trace it to the end. And this contributes to basically a lack of some overarching understanding of when should we be worried about this? When don't we need to worry about it? If we change our parameters, is that going to make this turbulence worse? Is it going to make it better? And so we're trying in our work, trying to give some sort of gross roadmap for these things that can then guide these expensive simulations. And I'll just say that these most detailed simulations will always have their place, because when you get down to it, you need to go into the nitty-gritty and try and tell what happens for your case. But it would be good to have more overall sense. So this is something that we're working on, basically building out a bird's eye, applying our work on compressing turbulence to build out a bird's eye view of the turbulence behavior in something like these National Ignition Facility experiments. And so we showed that you can come up with some stability criterion for the turbulence in these hotspots, and basically map in parameter space that you're operating in when you should expect the turbulence to grow and when you should expect the turbulence to decrease. You can also calculate basically a saturation level, which you can think of as how bad can your turbulence possibly get in these experiments. And if you compare what you get for calculating the saturation level to what they see in these most detailed simulations, you find that they're approaching something like 50% of the maximum sort of saturation level for the turbulence. So you can think of that's either good, in that it can't get much worse for this one than it is, or you could think of that it's kind of bad because there's a lot of room to do better if you don't want this turbulence. But in any event, this saturation level will depend on parameters of the experiment. And so then you can say, if we change our parameters, do we expect things to get worse or better? And then we're also working on modeling. Basically, so this is one of these plots of the energy against the compression. And this one I'm compressing from left to right. And the colored lines are simulation results, and the black dotted lines are model results from a relatively simple ODE model that we built without free parameters. And in the ideal world, then you would pair a model like this to 1 or 2D simulations, which will not capture this turbulence behavior, but are much less expensive for exploring the parameter space. And then you'll at least be able to get some sort of estimation for the expected turbulence behavior in these sort of experiments. So I'm going to switch gears a little bit. So I've told you about how turbulence could be an issue in experiments like this. But it's also interesting to ask whether we can possibly utilize turbulence to our advantage. And how would this work? So usually what we're doing in these experiments is we're starting with all the energy and thermal energy. So in this, I'm compressing, moving from right to left, and plotting the energy again. And we're basically trying to compress and steadily heat our plasma and increase the temperature until we reach some temperature point where it's hot enough for us to fuse, and it's late enough in the compression that we're dense enough to be self-heating. So we can think that maybe instead what we could do is purposefully start with most of the energy in some sort of turbulent flow. So that's the blue curve, and make our temperature much lower, the green curve, but the same initial total energy. So they add up to the red curve. And then we compress, and in doing so, we'll both increase the energy in the turbulence in the blue and increase the energy in the temperature in the green. And then at some point, when we're ready for fusion, we convert this turbulent energy into the thermal energy, and then we're hot enough to fuse. And if you look, by doing this, you see that over a wide region of the compression, we've actually kept our plasma cold. And by keeping it cold, we've reduced things like X-ray losses and also possibly other energy losses as well. So this scheme is a way in which you could possibly exploit this turbulence to your advantage. Of course, to do it, you need some sort of conversion mechanism so you can get this turbulent energy into the thermal energy at the end. And it turns out that plasma has a conversion mechanism like this, and it exists in plasma because of this strong temperature dependence of the viscosity that I mentioned before. And basically, so as you heat, you become more and more viscous. And so we're calling this sudden viscous dissipation. And the general idea is you're compressing this turbulent plasma that's amplifying the energy in the turbulence and also the temperature, and therefore also the viscosity. So if you look at this cyan curve here, we're starting on the right, and we're compressing as we move to the left. And the energy increases, and then dissipates very suddenly. And we can look at what the flow field looks like during this process. So we start at A here, our initial condition. This is a slice, basically, through the simulation box. We have some complicated flow field. As we progress to B, we see that the energy has amplified towards like higher values here. This is the magnitude of the velocity. And that we've lost some of the fine scale features in the flow. And then at C, we've lost even more of the fine scale features in the flow, and we've amplified even greater. And then at the end, we've dissipated. So ideally, we have an animation of this. So we can see the same thing happening here, plotting the energy, moving from left to right. Yeah, so we can watch it a few times. Basically, the energy amplifying and then vanishing. I'll move on because this is So we can understand what's happening here. This is maybe one of my more technical slides, but as we compress, we're basically putting energy. So I have large scales on the left here, small scales in the flow on the right here. The compression is a forcing, and it puts energy in at the largest scales of the flow. And those large scales of the flow are also where the energy in the flow resides. So as we compress in time, we're moving down. We keep dumping energy into the largest eddies in the flow. At the same time, the temperature is increasing and the viscosity is increasing. And the viscosity is acting at small scales to remove energy from the flow. And basically, as we keep compressing, the scales of this removal keep eating their way up towards larger scales. But the energy will only dissipate when this removal scale hits the large scales where all the energy is in the flow. So that's what's happening, and we saw that reflected in the scale becoming less and less, the flow becoming less and less fine as we progressed. So this gives us our mechanism by which we can imagine carrying out this new sort of design for inertial fusion experiments. And so I've been discussing basically strongly heated compressions where we can cross between an inviscid regime and a viscous regime. But there's also applications where basically they're inviscid throughout the compression. And this will be these molecular clouds, which I'll talk about now. But using our understanding of these viscous effects, there's actually some interesting results we can get for understanding the inviscid case. OK, so molecular clouds. This is a telescope image of one. And it's basically a large cloud of partially ionized gas in space. They're very highly turbulent. So they have a turbulent Mach number of an order of 10, and very, very inviscid. They have a huge Reynolds number. And these clouds of gas are compressing under self-gravity or also possibly from external like pressure waves. And these are regions of the regions where stars form. And basically, this turbulence affects the density distribution in the gas cloud, and that density distribution then affects things like the star formation rate, which is something that people can measure, like what rate do stars form in these clouds. So here's some simulation results, not by me, of this sort of molecular cloud turbulence. In this simulation, you're plotting the density, the plasma density, and you're moving from left to right as you compress. And as you compress, you're once again putting energy into this turbulence, and that's changing the density distribution. So roughly speaking, if you started here, you're this red curve. So this is the probability density distribution of the density on the x-axis. So you start something at this red curve, and then as you compress, you're moving towards the green and then towards the blue. So what's happening to the density distribution? Well, you're getting more and more likely to have very underdense regions. So you can see these holes of density in this simulation. But you're also getting more and more likely to have very high density excursions in the tail of the distribution function. And these high density excursions then are going to impact star formation, because you get this very dense cluster of gas, and maybe it will collapse to form a star. And so this density distribution is closely tied to the energy in the turbulence. So people are working on models to model the energy in this molecular cloud turbulence as it compresses under gravity. And I said before that you can use this, your understanding from the viscous problem, to even in this inviscid case. And basically, we created a class of bounds on the turbulent energy. And so here I'm showing, once again, here you're compressing left to right. These are simulation results and bounded by two bounds, which I've come up with, basically above and below. And we can apply, so these are viscous simulations where the viscosity grows, but you can also apply these bounds in the inviscid case. And we've done that to this existing model for the molecular cloud turbulence. And what you find is actually that the simulations and the model to which they're matched actually overestimate the amount of dissipation in this turbulence. So basically using this as a validation tool for these simulations, or this model. And what this means is that actually, compared to the model, the model is under-predicting how much the turbulence will grow as it compresses. So this is an area that we've worked, an application area that we've worked on. And as my final application area, you can wonder, I just talked about this supersonic turbulence that's happening in these molecular clouds, and we actually found that similar turbulence exists in some of the lab experiments that are already going on. So these are Z-pinch experiments, and these are basically done to generate X-rays. And those X-rays then can be used for various different applications. So in this case, you're compressing the plasma using a magnetic field, and you have this cylindrical geometry. So this is to give you some picture of what the compression looks like. And this is slices. This is looking side-on at one of these cylinders. These are experimental measurements showing this cylinder basically compressing in time and collapsing then to a column. And detailed measurements of this plasma column this is called stagnation when it meets on the axis, found that there's very large non-radial flow. So this is basically flow that's not associated with the fact that you're compressing, the radial motion of the compression. And we basically looked at these, the parameters and the measurements of this plasma, and found that if you treat it in a picture where this, basically that treating it as supersonic turbulence with some density distribution, basically a new picture of what this flow looks like, you find that if you look at all your measurements, that they have a better agreement. So the measurements in these experiments are very well diagnosed, especially for this kind of plasma compression experiment. So they actually have more measurements than they need to determine things like the density, the temperature, and so on. And so they're over-constrained. And with this model, this over-constrained problem becomes basically all the measurements are in much better concordance, and you're also physically consistent with what you're measuring about the flows in this plasma. And in order to do this, we basically had to work with the experimentalists at Weitzman to develop a new kind of spectroscopic analysis to account for the fact that you have this highly non-uniform density in this plasma, which you can predict this density distribution, and that's from work that a variety of astrophysicists have done. So we can put this in the context of this viscosity that I've been talking about. It's not really clear what makes these pinches so turbulent. That's still something we're looking at. But what we can say is that the plasma viscosity is enabling. Basically, in these X-ray generating Z pinches, you're compressing something that's a heavier element. And so something like, say, neon. And so you can ionize, and you do, as you go through this compression. And this increasing ionization state will basically tend to counteract whatever increase in the viscosity you get as due to heating. And I'll just note that, so in the fusion experiments, you're compressing hydrogen. You can only ionize once. So there, it's really the temperature behavior that's dominating you. So just to summarize, what I talked about, we have turbulent plasma compression, and this happens in a variety of different scenarios, both in the lab and in the natural world, in molecular clouds. And we basically need to understand what are the plasma impacts on the turbulence in these compressions. In this talk, I focused particularly on the importance of the viscosity, and basically conducting simulations and working on predictive models in these bounds to address turbulence in these various different applications. And today, in particular, I talked about this sudden viscous dissipation and new design concept, a bound on the turbulent velocity in application in these molecular clouds, and then also this new picture of Z-pinch stagnation as supersonic turbulence. So with that, I'll say thank you and leave some references for if you're interested in more information on this topic that I talked about today.